Well, hello friends, welcome back to DevTools hacking. Today we're going to keep looking at profiler stuff, and it's going to be about whole system profiling. So until now, we've only been able to profile one program at a time with our profiling system. So if we select File Manager Desktop here, for example, we can create a profile of the File Manager process, see what it's doing, but if we want to see a holistic view of what all the processes in the system are doing, then there's currently no way to do that. Like, you have to choose one process. And that seems like an unnecessary limitation. So today we are going to start building out full system profiling. And I think the idea is pretty simple, but the devil is in the details. So basically, the way profiling currently works is that if we look at our scheduler tick, which is this thing that gets called every couple of milliseconds by the timer in the CPU to interrupt the current task and schedule a new task, what we do here, before we go and figure out a new task to schedule, we will first check if the current process is profiling, and if so, we will go and append a so-called performance event or a perf event to the perf event buffer of the current process. So this is the basic mechanism, and we have these two syscalls, profiling enable and profiling disable. And the way they work is you call profiling enable with a PID, and it essentially creates a perf event buffer for that process and then marks the process as being profiled. And then whenever we run the scheduler, which is like every couple of milliseconds, if we're currently executing in a profiled process, we will generate one of these perf events and just stash it away in that buffer. And then later on, you can extract all of these events. Either you can go and pick them up in the proc file system. There's proc pid perf events, but also when a process exits and it has perf events, it will dump this thing called a perf core, which is what happens if you do something like profile-c text editor. So now we exited the program and we can see that there is a perf core file here that has been dumped, and you can open those with the profiler program. So that's what happens. In order to profile the entire system, though, this has to work a little bit differently. So I'm thinking, let's approach this in a very simple way. So we'll start with just some syscall here that, I guess, if you don't provide a PID, so if you say like -1, for example, we'll just profile everything. So we can put up here, if PID is -1. And then I guess we should only allow the super user to do this. So we will return eperm. Return eperm in that case, if you're not el super user. And otherwise, we will start profiling whole processes. Or let's call it profiling full system. True, right? Okay, and I guess we should probably, so we're gonna need some kind of a performance event buffer to stash all of these events into, because now we're gonna generate a lot of them, right? Because previously we would only generate a perf event whenever the profiled process was scheduled. And let me just show you what a perf event looks like, actually. So here is a typical, here's the performance event data structure. So it has a type, and then it has a stack size, which is like how many stack frames. And then we have the thread ID and timestamp, and then we have these performance events for malloc and free, and then we have a union of data, so just to not waste too much space here. And then we have all of the stack frames with a limit of 32 apparently. So this is a perf event, and there's finite space for these. So currently we allocate 4 megabytes of memory for the performance event buffer. Right here we can see that when we create one, we actually allocate 4 megs. So 4 megs is fine for a single process, like you can get a fair amount of profiling that way, but for the entire system, we're gonna need more than just 4 megs. So I think maybe what we'll do is we'll have a way to say like buffer size here, and then you'll have to specify, but it can default to 4 megabytes, or, you know, actually, let's reorganize this a little bit. So this has a big flaw here, that because we're doing this buffer allocation in the constructor, we don't handle allocation failure at all here. Like if this fails to allocate because we're out of kernel memory, we will just carry on anyway. So why don't we take this opportunity to make this better? Instead of having people call the constructor, let's allocate before we ever construct anything. So we'll make something like onPutter performance event buffer, try create with size. Yeah, that'll be good. Buffer size, and then we can hide this function down here in the private area. Still make it explicit though. And then we will go and let's see, what do we want to do in this thing? I guess allocate that buffer. So buffer is kbuffer try create with size, buffer size, and if that fails, we can very comfortably just fail here, right? Otherwise, we will adopt a new perf event buffer and move the buffer we just allocated into it. Although I guess we should release non-null because it might be null. Yeah, so the constructor here will instead take a non-null onPutter to kbuffer. Wait, is that how we use kbuffer? I guess that makes sense. Yeah, right. Okay, that's fine. And that's what we're storing here as well, so we can upgrade that one to a non-null onPutter as well. Yeah, that'll be good. And then, wait, why don't you like that? Let's see. Buffer. And I guess we had some more arguments here, actually, like the read, write, and allocation strategies and stuff like that. So let's actually copy this code that we already had. We'll just override the buffer size. Yeah, there's an important thing here to note, actually, that the page allocation strategy for performance event buffers is allocate now. Most of the time, we just reserve physical pages for memory allocations, but the performance event buffer has to be allocated right away. And that's because the next time we access it might very well be in the scheduler during an IRQ. And when we're handling a timer IRQ, we don't want to cause a page fault. So we have to actually populate this thing with physical memory right away, because we're not set up to handle page faults during IRQs. Oh, and I guess I have to adopt own that thing, actually. Yeah, so adopt own creates a non-null onPutter. Adopt creates a non-null ref putter. Maybe it should be called adopt ref. I don't know. Anyway, adopt own is where we are, so very good. And then, now that we've set this up, we can look for places where we actually construct these. So in process, ensure perf events, right? So this is called by the profiling enabled syscall. So we shouldn't trust this thing to totally work every time, right? Like instead we should do something like if process fails to create perf event buffer if needed, then we'll return enomem. Yeah, I think that'll be better. And then who uses this? Ensure, like this find usages thing in CLine, I feel like it's showing me way too much stuff, and I can't get a good overview here. Can I somehow expand all? Like, can you simplify this view somehow? I just want to see like one line per usage. I don't know. Anyway, let's not get caught up with that right now. So ensure perf events. Like I just want to see these. Profiling, right. Oh yeah. So I didn't mention this. So there's also a system call that allows you to inject a perf event of your choosing. So a process can insert any perf event it wants into its own perf events. And we already have that integrated with our malloc implementation. So you can set an environment variable, and that will cause malloc and free to generate perf events, and then those can be parsed by the profiler program to create a sort of a picture of what was allocated at this point in time. It's not something that we've used a lot lately, but it's something that we will use eventually for sure. Just that's what this is for here. So I guess we should have a failure case here. So if create perf event buffer if needed, if that fails, we didn't have memory for that otherwise. Yeah. So let's go and create this thing. So where is perf events? Right here. Yeah, so we'll just have that, and that should probably be private actually, because nobody from the outside should be calling this. And I guess we'll just put it in process CPP. Or where was the ensure function? Yeah, it goes here actually. Okay. So performance event buffer, try create with size. So for a process, we'll use 4 megabytes, 4 MB if you will. And if that fails, return false. Otherwise, return, oh, I guess we'll do this. Why don't you like this? Oh, it's not static. Got it. Right, and then, yeah, so let's do this change first, and then we'll get into the full system next. Because this is actually nice, because now we're covering up the case, or fixing the case where you try to profile something when you're just about to run out of memory. That is a very good thing to fix. So you're complaining about line 73 here. So the buffer can no longer be null because it's a non-null opener, so that's one less edge case. Very good. And yeah, so the actual capacity in terms of performance events in a performance event buffer is the size of the underlying K buffer divided by the size of a performance event struct. So the buffer size that we pass in is not the number of events that we can handle, but rather the number of bytes we can store in these buffers. But even so, 4 megabytes, that's like, I don't know, like 4 or 5 seconds at least of 100% CPU profiling. So let's just get a Profilamundo. Cool, everything still works, that's good. Great, so let's commit these changes, because I think these are just nice standalone changes anyway. Did I forget to remove that? Yes, I did. Okay. And I'm supposed to commit over here, which I keep forgetting. Kernel. Don't handle allocation. Ooh. Better handling of allocation failure in profiling. If we can't allocate a performance event buffer to store the profiling events, we now fail sys profiling enable and sys perf event with enomem instead of carrying on with a broken buffer. Yeah, so I think, what are you complaining about here? Typo? That's not a typo. Save it to the dictionary. That's a real word. Okay. So the next step here is, I guess, to add the global profiling flag. So let's see about that. So where does that go? I guess we can just have a global variable for now. So we'll put that with profiling, like next to the syscall, I guess. It doesn't really matter at this point. So what did we have here? We had profiling full system. Maybe we should call it all threads. That's slightly correcter. Cool, G, profiling all threads. Cool. And then the big thing that we need, actually, before we set that flag, is we need a perf event buffer, performance event buffer, but a ginormous one. So I guess global perf event. Oh, should we just call this like global profiling? No, profiling all threads is more descriptive. I like that better. So performance event buffer, try create with size. Let's do, I don't know, 32 megabytes. We'll start with that. Yeah, so let's try that. And, actually, I wish I had, wish we had a place to stash these, but I guess we're just gonna have to leak it for now, because we don't really want to use startup time constructors for this type of thing. So for now, let's just do this. Global perf events, yeah. And then like if there's already a thing, then clear it, else create. Okay, and then let's maybe put this in a critical section, because it would be kind of gnarly if the scheduler comes and interrupts us during this whole affair here. So let's just make sure that that doesn't happen, and we will do the same corresponding change down here in profiling disable. So if you're -1, you are the super user, then we will simply turn off this thing, and we should be good. So then in the scheduler, when the timer ticks, here, I guess, so profiling all threads. I already forgot what the other one was called. Global perf events, right. So like if global, profiling all threads, then we should most certainly have a global perf events pointer. This becomes an else if case, and then global perf events, and then we just do this thing right here. Let's see. Yeah, so adding a sample to it. It needs to know like what process we're in and stuff like that. But I guess the perf events buffer could figure that out. Does it know what process it belongs to? No. It's passed in when we serialize it. Yeah, this is gonna get a little. There's a bunch of things we're gonna have to fix here because until now it has. There's always been like, and there's only ever one process being profiled, so there's no need to keep track of which process is this sample in, and like what was mapped at which memory address in that current process. But that kind of changes now. So performance event buffer needs to also keep track of memory mappings, I suppose. Okay, well, you know what? Let's just do one thing at a time. So we will progress forward one step at a time. So maybe we can reorganize this actually. So performance event buffer perf events. Yeah, and then we will simply do this, and if perf events, then that. Cool. So yeah, a little deduplication here. But essentially, these two can move up here. All right. So now that we record back traces in every running thread, then we need to have a way to extract this stuff from the kernel. So we can't really dump a perf4 anymore because that happens on process exit, and everybody's not going to exit, right? So, and also we don't want to produce like a perf core for every individual program that was profiled, but rather we want like a whole system profile all bundled up into one thing. So I think what we really want here is a proc file system entry. So in procfs, here is proc pid perf event, which does this for an individual process. So the way it works is we find the process that this pid perf events inode corresponds to, prevent interrupts, and then serialize the perf events buffer for that process to JSON, passing in the PID and the executable path, which are then included in the JSON output. So I think what we're going to do here is we're just going to add a new proc file. So we used to have a profile, we used to have proc profile before it moved into proc PID, but I think maybe we can bring back proc profile. It's just that it will be like the full system profile. So we just forgot to remove this previously, that's why it's gray here. I think we'll just bring it back. It will become our full system profile thingy. So we'll put it maybe here. Profile. The proc file system is a slightly confusing place, but essentially it's based on callback functions that serialize kernel state into a buffer. And the last entry here in these structs, the last entries are the callback functions. So this one is going to be called profile. And we'll write it here. So profile. So we get the inode identifier, but we don't need that because we know that it's proc profile. It's not per PID. But we do care about the buffer builder. So we have a builder. And now we're simply going to, let's see, I guess we need to get the that perf events buffer that we were talking about. Extern, this guy right here, global perf events. Okay. So if we don't have it, then we can just actually return false. That's how you signal that we can't read this. There's some error reading this proc fs file. If things are good, we will return true. Okay. And now what remains is simply serializing this thing to JSON. Actually, maybe that returns something, because I think, yeah, that's what we were doing down here. So to JSON, and we pass in the builder. And we can't really pass in a PID or an executable path because we don't have those things. So we're gonna have to figure that out some other way. So to JSON, maybe we'll call this, or to JSON is fine. Global perf events. Okay, so this one, okay, buffer builder becomes like that. Used by full system profile, proc profile. Yep. Okay, so what does this thing do? Okay, so it looks up the process from the PID and then grabs the process space lock so that the process address space cannot be changed while we are serializing this stuff. And then we create an object serializer and print out the PID and the executable, and then we also dump out the address space. So I think what we're going to need to do here is for the full system profile, we're going to have to dump out all of the processes that are part of the profile. We're going to have to we're going to have to change the JSON format of profiles basically, because currently the PID and the executable path, they're like top level entries, but we're going to need to make like a processes array at the top level of the profile. I think that'll make sense. And then in there, we'll store PIDs, executable paths, and memory layouts, these regions right here. But for now, let's just make it so we can serialize one of these things. So I think down here is the actual meat and potatoes of serializing the actual events. And up here is just the profile specific stuff. So maybe we'll split this into a separate function. Something like to JSON impl, like that. And it will take a serializer. Like that maybe, and let's see. Because the JSON object serializer is a template class that can target any builder. We have two builders. We have string builder and kbuffer builder. So you don't see it here, but it's actually templatized based on the input here. That's why we need to templatize the serializer here. So we'll do serializer, call it object like they do down here. And then we move the aforementioned meat and potatoes up to there. So to JSON impl object. Like that, I think. Yeah. Yeah. Okay, that seems okay. Oh, I didn't actually add the new variant. So that is performance event buffer to JSON. This one right here. To JSON impl object. Okay, so let's see if we can capture a full system profile and then get some JSON out of proc profile. That would be cool. So we have to be root. Now we will enable profiling for PID -1. So this should be capturing stacks for the whole system. We'll disable it, and proc profile is there. And let's cat it. Ooh. Okay. we have stuff. Let's JP that so we can see what it looks like a little bit better. All right. So TID is thread ID and it's 0 in all of them. That's a little bit suspicious. I feel like it should be something other than 0 sometimes, but maybe we're not populating that field. Let's see. Let's use Tom Nom Nom's Gron tool actually. Grab TID. Yeah, so they're all 0, right? Yeah, so something is preventing us from setting that correctly. And where do we normally populate it? Performance event type la. Where would we be setting the TID? I have a hunch that nobody's actually setting it. Also, what the heck is this? This doesn't seem related at all. Okay, where is this even? Crash Demon. Okay. ClangD, you silly. This is not the same TID. Why are you confusing them? Anyway. So I guess just nobody's setting that. But we can set that. Where do we set the timestamp? Event.timestamp. So here we just get the current uptime in milliseconds. Sure. So we can easily just smash in the TID here as well by just doing thread current TID value. Let's see if that works actually. So we haven't done any multi-thread profiling either. Like now we're doing multi-process profiling, but we haven't done multi-threaded profiling before. So I guess we just never got around to profiling something that was interesting in that way. But now we have to deal with all of it. And I keep forgetting what I'm supposed to do. Proc profile. Okay, so now we have TIDs here. So let's run that and grep for TID. Cool. So actually, you can see that a lot of these have TID 0. 0 is the kernel process, which is the idle task. So we're actually capturing idle, we're sampling idle time right now as well. And that's really going to bloat up our buffer. So I think we should probably opt out of that at the moment and only capture samples where something was scheduled. Because, yeah, I mean, it's nice that we're idle as much as we are, but just in the interest of capturing interesting profiles, let's not capture the idle task for now and leave a fix me about maybe making that an opt-in mode, for example. Like you could imagine having, because it can be really interesting to capture idle samples as well, but it's also more costly. And yeah, so I'm just going to disable idle frames for now, and we'll probably get back to that at some point when I want to use them for something. So here, for profiling all threads, let's say if, do we have a pointer to the current thread? Right here. Tid is 0. Oh, do we have a way to look up the kernel here somehow? Kernel process. I was thinking like maybe some of the surrounding code was already looking at this. Because what I really want to know is like, yeah, this is what I want to know. If the thread is the current processor's idle thread, that's really the more correct check to be doing. So current thread is not. Fix me. We currently don't capture sample, collect samples while idle. That will be an interesting mode to add in the future. Yeah. Let's see that works. Because if we capture the idle stacks, then we're just going to bloat this thing up immediately. Previously, like the single process profiling mode obviously does not capture idle stacks because you would enable it for something you will never enable it for the idle thread because you can't do that. So, oh, right. Okay, and proc profile. Yes, now we only have 18 events instead, so substantially fewer. But if we grep for tid, we can see that no tid zeros anymore. So very, very good. Okay, so I think I'm happy with what we have here so far. We're going to commit this. Actually, let's just verify that we didn't break the old mode. Yeah, we're still good. Okay, and let's commit in CLion. Start work on a full system profiling. Calling the super user. Now call sys profiling enable with PID -1 to enable. Wait, I can't see the breaking thingy here. This is the 72 character, 72 column marker here. But like if you do this, you can't see where it is. So we got to expand a bit. All threads in the system, all running threads in the system. The perf events will be collected, are collected in a global performance event buffer, are currently 32 megabyte buffer in size, let's say, yeah. The events can be accessed via proc profile. Also, we should make sure that that thing is super user only, actually. But I think it already is. Yeah, right. So only root can see that thing, which makes sense, I think. This is none of your business if you are not root. Okay. Cool. Anything to note? I guess no, that's probably pretty good. All right. So let's start looking at actually opening these things in the profiler program. So what we want to do now is change the format in such a way that the profiler can make sense of it. Because if let's take a look at generating a profile the way it is today and what's actually in one of these files. So we now have our perf core here, and if we look at that up top, we can see that we have at the top level we have the PID, and then the executable path, and then the memory regions in that program. So as I was saying earlier, like we're going to want to move this into sort of a processes array or a threads array. Processes array, I guess, makes sense. And then we'll need to dump the executable path and regions for every process that we've captured stacks from. Also, it seems like the more pager program is not working quite right. Also, I cannot break out of it. Well, now we made the shell sig quit, or made it quit here. Okay, well, this is not good. We need to improve our more program. But anyway, let's change the format of the profile. I think we can make a change that then remains compatible with single process profiling. Obviously, we just need to like produce an array instead of put these things at the top level, because we can still leave all of the sampled stacks in a top level array, because you can go from each sample's thread ID to the relevant process. Like you should be able to look that up from the processes array. But yeah, so let's move that into its own thing. So I think we're gonna have to change the way the performance events are stored a little bit, maybe. Because it's not obvious when we should capture the memory layout of a program. Because if you capture it the first time you get a sample of a process, then it hasn't been dynamically linked yet. So you don't even have all the libraries loaded. So you need to capture it later on when the memory layout has all the code loaded. But how do you know when that is? I guess... No, this is a bit tricksy. I guess when a process dies, it could check if it's contributed samples to the global profile, the global perf events buffer, and if so, it could sort of, in its dying breath, add all of its memory regions to it. That would be one option. Another option, which is terrible, would be to do it on every time we capture a stack, but that's just going to be extremely inefficient, way too much work. Another option is that we would just do it on when we actually collect the profile, but then we would miss programs that have exited, which is not good. Because one of the things that I want to do with this is be able to do something like compile something, right? So compile a package inside Serenity, and then look at the whole system profile to see what was actually going on. Like first we ran make, and then make spawned a GCC process, and that spawned a CC1 process, and that spawned a linker in the end, and blah, blah, blah. And you want to be able to see that whole chain, right? So we'll have plenty of exited processes in our interesting profiles. So I don't think it's enough to just do this on exit, or to just do it when we actually serialize the perf events, but rather I guess one thing we could do is when the dynamic loader, right before it calls into main, it could give a hint to the kernel that like, oh, this process has finished mapping its executable code. Now would be a good time if you are profiling to capture the state of the address space. Maybe that's what we should do. Although it still doesn't perfectly cover like already running programs, or like if you start profiling while a program is in the process of dynamic loading, but it's not yet finished. Or actually, no, that does cover that. Yeah, maybe that is the best. It's a decent option. But if something is running and it's already loaded, then the first time we sample it will also capture the address space. Yes, I think that's good. So basically there will be a way to sort of seal the address space for purposes of profile capture. Yes. We can do something like that. We'll try that, and maybe there are better approaches that we can think of later, but we have to start somewhere. So essentially, we can probably take advantage of this thing we already have. If we look in the dynamic loader, right before we call the main function of the loaded program, right here, we call into the entry point. One of the very last things that we do is call msyscall, which this solidifies with the placement of libsystem, which is the only library in the system that's allowed to call the kernel. So the very last thing we do here before we call main is to call msyscall. So we could just hook into msyscall, I think. Yeah, when you call this thing with null, we start enforcing the syscall regions, and this is the point where we want to capture the address space layout for profiling. So if g perf events, what was it called? Global perf events. Yeah. Although now I'm getting ahead of myself because I wanted to do something else first. I wanted to do the part where we just change the format of the JSON. But then I got into this instead. Okay, let's do the JSON thing first, because otherwise it will be hard. If we do this first, then it will be hard to get those things into atomic commits. So, and I would like to do that. So let's do the JSON thing first. So let me just write a quick note here to self that what we want to do is capture the executable address space layout of a program, of a process at this msyscall, and store it in the global perf events buffer. For processes sampled that already had that had already called msyscall, capture their address space layout on first sample. Yes, that is the what we're gonna do with that. But let's do the JSON thing first. So when we dump out this JSON stuff right here to JSON, then, oh yeah, right. So we need to change the struct. So here it needs to have or it shouldn't be a performance event, but rather a separate thing. Like sampled process, let's say. So in here we'll store a PID. And an executable path. And the memory regions need to go in here. So what do they look like? It's essentially a name and a range, right? So regions has name, base, and size. So yeah, it's the name and the range. That's it. Everything else can be worked out from that. So sample process will have struct region, which has string name and these don't need to be packed. It's not such a big deal, actually. Sample region range. Yeah, that's it. That's what goes in there. And this does not need to be seen outside, so we'll just put that in here. Do we need to track the TIDs that belong to it? I think we do. Although, okay, wait, hold on. Sampled process. I think we'll store these in a hash map. PID T. Wait, can we have a hash map from a process ID? I don't even know if we do that kind of thing. Seems like we can do that. Okay. Sampled process. Maybe we'll store it that way. Processes. Yeah. So you look up a process, you find this thing, and then in here there will also be a vector, or you know what, let's just put a hash table thread ID threads. Cool. This is all the information we need. And then when we do this thing right here, we are not going to we're not going to serialize this on the fly, but rather it will have to be It'll have to be done somewhere else. So to JSON. This whole thing needs to disappear actually. So in procfs, where we call this thing, which is here, then I think what we'll do then is we'll simply do this, and then that information has to have been already stored in there. Although who does that? So when you start profiling a program, like when you do profiling enable, I guess we would have to do it then. Here, so perf event buffer, add process. Yeah, let's do this. Collect or add process, let's say. And let's make it a const process, because we're not going to mutate the process. We're just going to collect some personally identifiable information about the process. So, let's see first if we already have it. Or I guess we can, when you call this, we'll always either update or replace the existing information we have about the process. Although we don't want to lose any threads that may have been killed. Maybe we'll ignore the killed thread issue right now. Yeah, I think we'll leave a fix me about that. What about threads that had died? And then we don't need this, and then we can just do sampled process. And then let's see if we can initialize that. So PID is process PID. Executable is process executable absolute path. I think we need kernel file system custody. Is that not what we need? Oh, maybe I should have stored this as a process ID actually. It's a pointer. So I guess we'll do something like this then. Fine. Is that a complicated getter? No, it is not. Okay. And then threads, we'll just fill that in momentarily. Process for each thread. Sample process, threads set, presumably thread tid. I think that's how it would work. Should we do that even? No, it looks better that way. Okay, and then finally, processes set, process PID, move sampled process. Oh, and this expects an own putter. actually. No big deal. There we go. Okay, so that's probably good. And then, well, we also need to capture the memory regions, and I forgot to make something of that. So regions. There we go. So let's see, let's take a lock on this guy. That will be process space get lock. Just lock that pupper. Oh, it's a spin lock actually. Spin recursive scope spin lock. And let's take it here. Okay. And then we'll be in and out pretty soon. Then we just need to walk the memory regions of this thing. So do we have regions? Sample process regions append. Name is region name. Range is region range. Cool. Nice and tidy. This code actually looks really tidy. I don't know why. I just I like the way it looks today. Okay, so let's use that stuff now when we serialize. So instead of doing this gunk, we need to start walking all of the things that we have. So, and let's actually put that up here. So for process in in processes, sure. And then we want to start an array. So object add array. Call it the processes array maybe. Okay. And now we will add an object, process object. Process and object. My brain wants to turn that into project, which in some way makes sense, but it still doesn't. So, wait, do we need to name this object? No, we don't want to name an object. That doesn't even, it's not a thing. Just add the object, and then we want to add keys to it. Should give me a serializer. Yeah. Then I can add PID, process PID. No, what's in there? Oh, right, it's a pointer. Can we avoid that being a pointer by doing this, perhaps? Oh, wait, it's a hash map, not a hash table. So process is it value. Yeah, that's what we want. Okay. So PID executable, and then the regions. Oh, there we we go. Finish. And what comes next? Regions array is process object add regions. Yes. Add add array. That's what I want to say. Yeah, I'm not super used to using these JSON serializers, but they are awesome. It's basically, it allows us to build up a JSON tree step by step without actually building a tree in memory. So it's like they're just serializing the string into a text buffer. It's a very awesome classes by Sergey. I think Sergey wrote these. Very, very cool. We used to build up entire JSON object trees in the kernel, which was very time consuming. So he came up with this serializer templates that they just append characters to an arbitrary builder class, so you can use it with either string builder or kbuffer builder. Very cool. Okay, so we want to build the regions array. So I guess JT then, process regions. Region is JT dot, oh, wait, I don't need to JT that. These are just regions. Regions array, add object. Also, will these things not finish implicitly on, yeah, they finish on destruction if not already finished. So I don't actually have to do that. That's kick-ass. But I probably do want to finish here, otherwise it won't be destroyed until after this. Yeah. So here I need to do that, but okay. Set name. Region name. Base range. Base get. You don't like these? Because it should be add. Okay, I'm really struggling to remember the API, even though I literally just used it. Okay. And then we can get rid of this whole thing here. Oops, excuse me. 204. Missing initializers. Well, aren't you fancy? So I'm missing initializers for regions, I guess. And then what am I not doing nicely? Not returning an iteration decision here. Just continue. And then what? Oh, threads as well, right. And then they need to be in the different order. And now what? Oh, we're actually calling to JSON somewhere. To JSON. Would that be when you finalize it? Where do we dump the perf core? Dump perf core. That's probably where we're doing that. Yeah. So when we dump the perf core file on process exit, we use this one, but we shouldn't need to do that anymore. So we should just be able to simply to JSON. Although this is an alternate version of the API. Wait, so oh, but that guy calls that goofy API. Oh, okay. So that's fine. That's fine. We'll just do it this way. Get rid of this API. And we can also get rid of that API. And now you have these two. You can use whichever one you like. Also, this one could probably be const if this one is const. Because why not? It's weird that one is and one isn't. Let's make it const. And what are we missing now? This thing. Oh, that doesn't exist. Oh, wait, did I just nuke that? Or I'm confused. Maybe we shouldn't even offer that as an API. You can just make your own buffer. So we'll do this, and then the perf core generation thingy just can just make a buffer here. So we'll see buffer. Okay, buffer. Try create with size. How much space do you need? How much space do we normally allocate? What's the default of this thing? Is there a default? Okay, buffer builder uses 4 megs. Okay, well that's fine. Oh yeah, let's just do it this way. Yeah, kbuffer builder, by the way, is kind of a dumb API. Because it also has this flaw that it will allocate a buffer and it has no way to tell you that something went wrong. So it's a very confusing API, and we should probably get rid of it, but not at this very moment. Right now we have something else that we're doing. Yeah. Process CPP 456. Something is wrong here. To JSON. Oh yeah. So at least now we should be able to capture a profile and see that the JSON looks good. So let's just capture some desktop action here, just selecting a bit. And sure, he didn't like that. I should have thought of that. We'll do it this way instead. Exit, and we do get a perf core. So let's take a look at this magnificent thing. So we now have a processes array, and here is one entry, PID29, executable bin profile, and all the memory regions in that thing. Looks very good. So that's really cool. So let's see if we can just trick it into doing it on msys call as well, or actually, no, let's not get ahead of ourselves. I keep trying to get ahead of myself. First, let's make the profiler program actually understand the new format. So in the DevTools profiler program, we have the profile class, which is responsible, as I recall, for load from perf core file. And it's going to fail right here. This is where we failed now, because it looks for a PID key at the top level object, and also for the executable key. So instead, we now need to look for the processes. So if object has, it doesn't have processes, then return string invalid perf core format, no processes. Yeah. And then we need to actually go and gather up all of these processes. So same concept actually as in the kernel. So I guess we can just grab this thing here, because now we're going to soak this up. Maybe we will put this in the profile class declaration as a private class. Of course, this can just be PID-T. These will just be ints. And here we'll have a base and a size instead. But yeah, other than that, we're good. And we'll call him process. Okay. So now to actually populate this thing. So, or object get processes. If it's not an array, or actually, let's do that separately. Get processes. Maybe this, we should have done it this way. Processes value. If we don't have that value, yeah, then we don't have to do multiple lookups. Look at us being good boys, avoiding multiple lookups. Although null is a bit weird here, so object get, I mean, that's okay. That's okay. If processes value is not array, processes is not an array, as array values. So now we can iterate the process values. Okay, so if process value is not an object, then let's fail again. Invalid perf core. Process value is not an object. This is kind of tedious, but it'll help us. It might help us catch something going wrong, so I'm just going to do it. Process value as object. Okay, at this point, now we're just going to make some assumptions. So, vector processes. process, sample process. PID is process get PID to U32. Executable is process get executable to string. Threads is regions is Oh, should that be an I32 maybe? Yeah, okay. Yeah, we'll do that. Okay, and then we need to also get all of the threads and regions. I feel like I didn't actually export all the threads. I suppose you know what? I'm just gonna skip over the thread part right now and focus on processes, and then we'll have some fix me's about threads anyway. So we'll focus on regions instead. Process get regions. If it is null, then invalid perf core format. Regions is no regions for process. That doesn't look good. Actually, we can even say if it's not an object, or array rather. Yeah, and then let's do that first, just to get that free sanity check. For auto region in regions value as array values. Sampled process regions append. Region get name to string. Base is region. Oh wait, these are values. We need to make them into an object. As object. Okay, here we go. Size is region, get size to U32. Cool. And then finally here, sample processes append, move sample process. And we will have all of those boys collected. Cool, and then we can get rid of this. And the regions are now per process. Library metadata. Okay, so this has to be kind of reorganized now. So the profile needs to keep track of processes, and each process has library metadata. So maybe we'll move this up actually. Okay, so library metadata is a member of process. You can't be there anymore. Executable path goes away. Event stays. Yeah, everything else kind of stays, but the processes change. Right. Yeah, okay. And then the constructor, I suppose we'll simply have to receive not the executable path nor the library metadata, but rather a vector of process. Yeah, this is what has to happen. And that's also what we will keep next to here, vector of process. Cool. Move the sample processes, move the events. And the library metadata goes up here somewhere. Let's see. Regions values. Oh, wait. So it wants the value, but that's okay. Oh, yeah, that's fine. We can actually do it that way. So then we just pass it in here. Library metadata is boom. It's kind of awkward looking, actually. Can remove the M underscore. Also, this thing should probably be renamed to like object metadata, or I don't know exactly what to call it, but like because it's not strictly for libraries only, we also have an entry for the main executable. So library metadata is a misleading name. Anyway, that's cool though. And then I feel like we were using that down here, yeah. So here we need to know which process we're looking at, but we can do that by looking at the thread ID of the sample, so or of the event rather. So let's just collect that. So event, we don't even catch that at the moment, but we will start doing that right now. So do that, and then perf event get tid to i32. Yeah, there we go. Now we have the tid. And then what did we do with that? So yeah, as I was saying, we're going to skip over the part where we have multiple threads in the same program, and we'll have to come back to that later and fix that. But right now, we're just going to assume that there's one thread per process, which is obviously not correct, but it will allow us to move a lot faster. So the library metadata, first now we have to look up the sample process in the vector of sample processes. So sample processes find first. Wait, what do we have? I'm trying to remember what kind of API we have. First matching, that's what I'm looking for. What does that return? Optional T, that's good. Entry dot pid equal to event dot tid. Fix me. This doesn't support multi-threaded programs. Yeah, and then if process has value, then let's see, library metadata. Yeah, that's really kind of gnarly, but makes me, this logic is kind of gnarly. Find a way to clean it up. Yeah, but still though, that's okay, I guess. So we'll just do a linear scan through the vector of processes, find one that has a PID, matches the TID of the event. The main thread of every new process has the same thread ID as process ID, so we're just exploiting that fact here. And then let's fix this constructor. Cool. And I don't know what you're complaining about, but I think this is some clang thing, so I'm just gonna fix that up. Okay. I should try to build in C-line more often. I'm just keep forgetting to do that. But it is nice to be able to click on the errors. Profile has no member libraries. Right, it doesn't have that. Because we removed that. So this is the disassembly model. Right, so this guy now has to, instead of looking at the profile libraries, we have to look at the relevant process for the current profile node. But every profile node belongs to a specific process, so that should not be a problem. Do we have the profile class here? I feel like we don't. Oh, it's below us. Okay, so what we want is we just want to get to the process. So we can give every profile node a PID. I think that would be okay. Every profile node can just know which PID it belongs to. No big deal. MPID, let's say. And when you create one of these bad boys, you gotta provide the PID, dude. You got to provide the PID. Right here. Okay, and then in the disassembly model of theme, we can't do this, but we can get the process like, actually we should have an API for this. We should have something like profile node dot process. Okay, let's yoink this and put it up here. We'll make it a lot more friendly, and I think we'll yoink the library metadata as well, just because. Because why not? Then here you need to provide a PID, son. Okay. And how dare you call it without a PID? And now we're cheating again, using the TID instead of the PID. Fix me. More cheating with mixing. Intentional mixing of injected PID here. Yeah, yep. And then this thing also needs the PID. All right, well, these changes are very, very mechanical, so not even really thinking so much about what I'm doing. I'm just like fixing the breakage consequences of moving those two classes out of the profile class. So we should be good there, and then now we have process at the top level, so we should be able to provide an API on the profile node, which is a node in the call tree, by the way. So here now we should be able to offer const process, something like that. Which, of course, wait, how do you do this? Like this. Can we get to the profile from the profile node? Wait, can we not? Profile node doesn't have a back pointer to the profile. I thought it did. Okay, all right, well, no big deal. We'll just do that. A little bit of a sneaky trick that you can do in C++. If you don't have a pointer to something as a member, you can always just take it as an argument. Processes, profile, process, find process with PID, yes. And then we'll give him an API to look it up. It's all coming together. I guess we can just do like M processes first matching. Value or null pattern. Okay, and what did I screw up here? First matching is non-const. Come on. Let's cheat. I don't want to go and change vector right now. Okay, and why don't you like that? Wait, what? First matching. What does this return? Oh, wait, it returns it by value. Oh, that's not what I want anyway. I didn't want it by value. I wanted an iterator. Do we have find? We do have find. But find takes... I want find if, right? Yeah. Okay, I'm not used to find if. Somebody else added it, but it is nice. It's just that it's not in my brain yet. So find if returns an iterator, right? So M processes find if entry PID is PID. Then we have the iterator, and if IT is end, return null footer, otherwise return IT. No, how does it work? The process is right there. Okay, wow. That is really awkward looking. Does this help the situation? Maybe slightly? Maybe there's a much better idiomatic way of saying what I just said here, and this looks really dumb. I don't know. Anyway. What are we doing wrong on 312? Let's find out. I'm trying to copy construct a process. Oh, wait, is this the same problem right here? I wanted to find if. Oh, here I can just use IT arrow, right? Okay, and then we have this problem right here, but this should now be fixable because all we need to do is node.process. Pass in the profile as we said we would, and then arrow hoping for the best. And then library metadata is, ooh. So this is kind of rickety looking. I don't like that. Fix me. This is kind of rickety looking with all the Okay. And we have at least opened it, although it seems like we're not comprehending what's going on in here. So not super great, but we can see the samples. They are right here. This is what they look like. So what would it look like if we profile the whole system now? This is enable and disable, by the way, in case that was not obvious. Segmentation fault. Null pointer deref. Well, that is just a bit smelly. Let's get a crash reporter for that. And we are crashing in library metadata, library containing. So I bet you that we are calling this on a null pointer. Probably, is that right here? Or wait, where is that? Load from perf core file, actually. Okay. By the way, we should probably fix this thing. Like the fact that this is a segmentation fault and it's we crashed because of a null dereference, but that does not appear anywhere in the crash report. We should really display the address that caused the segmentation fault and like whether it was a read or write, stuff like that. Anyway, so library containing on line 438. This is crashy. Sure. So on 317, we're calling it right here. And I guess it's because this thing, right, because I'm stupid. So if it is, we need to be null checking this pointer before calling it. like that. That was dumb. Okay, let's try again. Okay, this is our full system profile. Of course, now we can't see which process, which PID everything is in here, or thread ID. We could definitely add a column to the samples here. That would be, I guess, the first thing to do with that. I think maybe we won't do the call tree aggregation today. We'll only do the samples view. So let's go and add a thread ID field here, or process ID maybe. I'm thinking like, what's the most honest thing to call it? Sample index timestamp thread ID. It is going to be the thread ID, so let's put the thread ID. Thread ID, oh, TID. TID is fine. Event TID, boom. I cannot wait to see that. That's going to be super interesting. So let's do something exciting, like opening a browser. Okay. So we actually see kernel frames here. That's neat. And yeah, you can see the thread ID. So very, very cool. We're now capturing stacks in all threads. And we can only see the kernel symbols so far, which is still very interesting. But obviously it would be even cooler if we could see the user space symbols as well. Very interesting. If we flip that. So it's so cool to see like the whole system. Even if we don't separate things by process here, it's still really cool to see like what is the most common thing across all processes to happen in the kernel. And it seems like that is in this browser launch test I just made. Select syscall, making a vector of ints. We can definitely improve that situation. There's no need for select to have a dynamically allocated vector actually, since select is bounded by the fd set size constant. So where's foot vector? In fact, wait, foot vector is already has inline capacity. Oh wait, it's a vector of int. Wait a minute. Okay, I'm just gonna allow myself to go down this sneaky little investigation here. Oh, look at this. This vector here doesn't have inline capacity. So we're actually hitting the kernel heap in select quite a lot. Quite a bit. It's like 3.4% of this, I mean, admittedly very random thing I just did, like just launching the browser, but even so, like, that's kind of interesting. And we have string allocations in directory traversal, looking pretty heavy. Interesting, very interesting. Oh, proc is all. That's cool. That's like reading proc all, which is read by this guy up here and this guy. They both read it separately. Could definitely do some consolidation there, like making a single process that draws both of them, for example, would be a start. And you would reduce this. Anyway, dude, we're gonna have so much fun with this feature, but let's improve it a little bit first. So we're still gonna need to see like what's going on in user space here, right? Because kernel symbols are super interesting, but we need to see the whole picture. So what is going on with the user space? Why can we not see what's loaded? So I guess because of the add process thing, right? Like we never actually populated that thing. So let's do that msyscall trick that we talked about. Finally, now is the time for that. So when you call msyscall, here we'll do the hack. If we're profile, doing a global profile at the moment, add this process to the global perf event. We do this here because now is a reasonable guess. Now we do this here because at this point the executable parts of the address space should be final. Mostly final. Yeah, because almost no programs actually add more executable memory once they've started. We actually don't have any program that does this right now, but in the future we might, but we currently don't. So what we want to do here is just check if we need that thing. So his name is profiling all threads. And his friend is Mr. Global Perf Event. And we'll put this in a scoped critical here. So scoped critical. Add process this. Okay, that's cool. And then we also need to do it according to what I wrote down. If somebody has already called msyscall, then we need to capture his address space when we first sample him. So that would be, I think we can do that without causing page faults. So scheduler, add, where does that go? Perf events. Okay, let's see. Let's put something in here. Maybe, I don't know, this is a little weird. No, wait, here we don't know if we're global or not. So we'll do it here. If current thread process space enforces syscall region. So if that is already true, then we need to perf events add process current thread process. So this would do it on every iteration. We only want to do it once. This is kind of awkward. Wait, okay, so what if we just do it every time now just to test it? What am I doing wrong? mmap, wait, mmap cpp5? Oh wait, I don't see that class declaration. Okay. How will this go? Okay, looking somewhat promising. Look at all these user space things. Oh, dude. Dude. This is looking very spicy. And even the call tree here actually totally works. It's just that we don't know which process is which because it doesn't aggregate per process here. It doesn't keep track of that. But we can see it here for the individual samples, which is just so cool. This is so neat. Why is this thing so wide? This thing could be much less wide. So what are we doing in user space? Let's see. Or what would be I was thinking, what would be an interesting thing to do? I guess let's try to make a new one where we do something like let's load Google. So do that, and then we open this thing, open google.com, and we stop the profile. So here we should be able to see all kinds of interesting stuff, like the browser launching, me clicking Google, and then like talking to the web server and everything. So many different things involved in this. And now we can see that libcrypto is the biggest user space CPU hog, clocking in at 13.66%. And of course, it's actually in the protocol server process, which we don't normally profile that much because I'm always like focusing on the browser. But now that we can profile the whole system at the same time, we can actually see into all of these helper processes. Yeah, you see here, protocol server is the program doing this. Oh, dude, I love this. This is so cool. Ah, man. I'm just so happy at it. I don't know what to say. Like this is my favorite new feature by far, and I'm going to use the heck out of it. There's the HTML parser, of course. Not looking terribly bad. Probably a lot we can do in the crypto library to make it faster, because it's the big int implementation that is soaking up the time here, and I think we have barely scratched the surface of like optimized big int implementations. Like we have some naive allocation avoidance optimizations, but like I'm sure that there's a lot of tricks and stuff that we can do to make this a lot faster. And you know, you have two of, are these actually calling each other or what? Divide calls both, yeah. So actually I guess we can flip this to get a top view instead. To see, oh, crashed the heck out of it. Well, it can't have everything. Can I get a, right, so crashed because of reasons. And this guy sure has mapped everything. Because, we'll just map everything so that we can disassemble it. But look at this guy here. He's like mapping the same library multiple times. It's kind of silly. We can certainly avoid that. Yeah. Anyway, I just got I got a little carried away just messing with it there. But how cool is that? Seriously. I guess we can bring it back right away. So neat. Okay, this thing where I click on something that's like wide and it scrolls the view, it's so irritating. I don't know why I never go and fix it. It's like you click on something that's not a wide piece of text, then it's fine. But if you click on something long, it's this very jarring horizontal scroll happens. I don't know what's up with that. But very cool. Very, 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 very cool. Maybe we should show the executable name here in this view also, not just the thread ID, but the executable, which would be cool. So let's do that. Samples model. Thread ID, executable name, let's say. Oh, wait, where is that even? We only have the event. Event. Oh, yeah, right, but we can cheat. So we can get the profile process for the event tid, which is, again, more abuse of the PID-TID relationship. Makes me more abuse of the PID-TID relationship. Yeah, so we'll try this. And if we don't find it, we'll just return nothing. The empty string. Still, I mean, this should be very interesting. And let's also verify that profiling a single program still works. I don't want to break that. I definitely broke that. Okay, cool. Samples model 65. I forgot to implement column name for executable. That's fair. Easy fix. Oops. Yeah, so this still works. Now we can see the executable right here. Very, very cool. And let's grab a big boy profile. And what do we want to profile this time? Maybe something that we rarely profile, like the fire demo. Wonder what it's doing. And you know, when you're running something like this, you also kind of wonder, what's the fire demo doing, but what's the Windows server doing? Compositing all of this stuff, like what kind of time are we spending on that? And previously, we have not been able to see that. But this should actually give us some ability to see that as well. So we can see here is actually the page flipping happening, triggered by the Windows server. Of course, quite aggressively, because it's just drawing at as many frames per second as we allow it to, which would be 60. And the blit is heavy. Oh, wait, that's cool. Procfs all very high up here. So these guys are kind of busy. Interesting. And we can see this executable here. This is just so cool. Man. Okay, I need to stop fawning over the code and make some commits. So what do we even have here? So we have converting the format. We converted the format of the thing, right, to have it as a separate thing. Okay, so now let's do that first. Yes, 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 and yes. Right, so this one is kind of questionable. When we tick, we now always update the process in the perf events buffer, so it's a little bit weird. But we'll live with it for now. But this is very, very good. Mm-hmm. 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 Yep. Mm-hmm. Yep. 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 Mm-hmm. Yep. Yes. Looks good. Yep. 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 You too. Yep. Even you. Yeah. So I'm only leaving out the msyscall hack, so we'll put that in a separate commit so I can explain it. Kernel plus profiler. Capture metadata about all processes, all profiled processes. Previously, the perf core file format was previously limited to a single process, since the PID executable regions data was top level in the JSON. This patch moves the process specific data into a top level array named processes, and we now add entries for each process that has been sampled during the profile run. This makes it possible to this makes the profiler, this makes possible to see stacks from samples from multiple threads when viewing a perf core file with the profiler. This is extremely cool. I'm even gonna add an exclamation point to that one. And here is the hack. Yeah. Actually, like, do we even need this hack at the moment? Because right now we're just capturing the process information on every sample anyway. So we could actually live without this hack for now. I think maybe that's actually a better option. Oops. And then we can think more about it, because it wasn't debilitatingly slow to do it this way, which I thought it was going to be. So I think we can probably live with this for a moment while we get a chance to think more about ways to approach this. And then we don't need to introduce this awkward hack and like do stuff in msyscall that doesn't really have to do with msyscall as it's supposed to be. I think that's generally a good idea. So let's do something else fun, like open a markdown file and have it load. It's very cool. And disable. And that is very, very interesting. So here again, libcrypto showing up because we that markdown file had a screenshot from the README, which it was fetching from GitHub because it's a GitHub HTTPS URL. So we can see that showing up here now. It's very neat. And where is even like markdown parsing? Does it even show up? I guess it's very not significant. Dude. Oh yeah, and the multi-process browsing stuff, like that's so much better to have this multi-process profile view, because now you can actually see all of the moving parts and what they do. And actually, if you recall, if you watched the video a week ago or so when I was profiling startup to figure out what was going on and try to improve startup performance, then there was this part where I couldn't see what was happening, because like it looked like in the profile like nothing was happening for a while, because I was profiling like the text editor starting up. But in this new world, if nothing is happening in one program, we should be able to see what's happening in other programs at the same time. So those kind of mysteries will no longer get in our way. That's very cool. Mem copy. There is just infinity things to investigate here. So cool. And anyway, let's not get carried away. So, but let's add a big fat fix me here. Fix me. This is very nasty. We dump the current process's address space layout every time it's sampled. We should figure out a way to do this less often. Yeah, because there might be some elegant solution to this. Like imagine that you had, for example, you could have a version number on the address space object, and then you could just increment that whenever you mutate the address space, and then you would just keep track of like which version of the address space you've cached or something like that. There are many different approaches we can take to this. I'm just gonna not care about them right now because we've been sitting here for a moment and I need to have a nice little break. So we are just gonna amend that to the previous commit. And maybe enjoy it one last time for today. Obviously, there's still various things to do with this, like making the tree view more process aware and doing multi-threading support, adding more UI to take advantage of all this new information that we have and find interesting ways to visualize it. Like you could imagine doing a timeline. You could split up the timeline per thread, for example, if you wanted to. So you would see every thread as its own timeline. If you're running in multi-processor mode, you could do one timeline per processor. There's so much stuff we can do. So let's profile the JavaScript test suite. And let's see what the system is actually doing while we are running it. Probably not much other than the JavaScript, but we can see here actually which programs are running. I guess one thing you could do here is you could allow filtering by process. So you could have almost like a checkbox for every process somehow, somewhere, and then you could filter which processes you want to see. So if you want to see all processes or a specific set of processes or whatever, or processes in a specific process group. Okay, so here we can see that terminal comes in, Windows Server. So other stuff does get scheduled while we're running test.js, obviously. I mean, obviously we have to repaint the screen and everything. Menu applets come in. And, you know, this is stuff that also obviously affects the runtime of JavaScript test suite. So it is really cool to see that. And here we have the taskbar because, of course, if you didn't notice, when you run test suite, if you look at the taskbar entry for this terminal, we have a progress bar that shows the progress of the test suite. A feature that I am very fond of. Anyway, I think this is going to be it for today. So I'm obviously super happy with this feature, and I'm going to keep iterating on it. But man, we are going to have fun with this. Very cool stuff. So if you made it this far, then I thank you for watching, for hanging out. I hope that you saw something interesting here today, and I think this was really cool. If you have some ideas for interesting visualizations we can do with this new data, then please let me know. Or if you profile the system and find something interesting, then please let me know as well. Anyway, I'll see you all next time. Thanks for hanging out. Bye.